So ask me if these maps were the first kind of maps which are maps drawn on a surface, or the second kind that are maps from space. And in fact, they're both. So you should read this in two ways. It's a way to draw maps, and it's also using maps as a drawing tool somehow. So as you will see, mainly there will be three parts, but the second one will be shorter than the other two. The first one is something I've been thinking about for a while, and some of you may have heard at least a big part of it. It's about probability and how to look at models on different kinds of lattices. And the third part will not be as such about probability. It will be about a tool which is known as Bailey functions or Bailey maps, and which are a way to describe conformal maps in a very explicit and very computable manner. So to make somehow the Riemann mapping theorem a little bit more explicit and a little bit more tractable somehow. So I will start with the first part. So the question is this. So you take your favorite lattice and assume, for instance, it's a triangulation. So this is your favorite lattice. It's Z2 with one vertex at the center of each square. So it's a triangulation of the plane. And the question is, you want to do statistical physics on this lattice. So you want to define the notion of scaling limit. You want to make a model on this and rescale the lattice to have a finite and finite mesh. And you hope that at the critical points, you will have something conformally invariant. And the question is, how do you want to draw this lattice on the plane in such a way that you do get conformally invariant scaling limit? So for this lattice, it's a little bit boring because it has a lot of symmetry. So the only thing you can do is to embed it using squares. And hopefully the beamer makes this into a square. Does it make it into a square?
Almost.
If it doesn't, the next pictures will be very wrong. But this is supposed to be a square. So there is no choice. You just have to embed it like this because it has to preserve the symmetry. So what about this? If you have this triangulation, you see it's the kind of thing we will look at. It's a periodic triangulation of the plane. So it has vertices, it has faces that are triangles, it has nice combinatorics. And the question is, if you want to do statistical physics on this kind of lattice, how do you embed it in the plane? Okay, so the first thing you might say is that, okay, if you do probability, you know about random walks. So maybe it's a good way to kind of measure the right embeddings. So let me just write something on the board, and I will complete the picture as we go. So the data, what you start from is this triangulation. So it's a periodic triangulation. So it has no geometric structure. It's just the adjacency between the vertices, and it has some automorphisms which are given by translations and which form a Z2. And what we want is a way to embed that in the plane in a natural way. And as you see on the picture, one way to fix the embedding is to choose this parallelogram here by fixing the two periods of the lattice. So the periods will be, we can always choose one to be equal to 1, and the other one will be tau. And tau will be in the upper half plane. So essentially, the one quantity that we want to choose in a natural way is this tau. And in the picture, this would be 0, this would be 1, and this would be tau, and we want to choose the location of this point. Okay, so let's do one thing. We can look at a simple random walk on our graph. So we have a lattice on the plane. We can look at simple random walk on the vertices, and we can state that for this simple random walk, it's well known that there is a central limit theorem. It's enough to have this periodicity. So there is a scaling limit of this, which is a Brownian motion, and it has some covariance matrix. And if the graph is chosen symmetrically, you expect the covariance matrix to be a scalar matrix. So that's what will give you a rotational invariance. So that's one thing you might try. You try to find an embedding for which you can tell that the scaling limit of the simple random walk will be rotationally invariant. So there is one natural way to do it. It's a nice exercise. You just first you choose the embedding in such a way that the random walk is a martingale. So that means that each vertex is at the barycenter of the neighbors. So this guy should be the barycenter of all the neighbors it has here. And you can do that by solving linear equations. So essentially, you have a way to do that, preserving the periodicity. And then, once you have this, what you have to do to have a scalar covariance matrix is to do this. You compute on one of the periods the sum of E squared, but where E squared is the displacement along one of the edges, seen as a complex number. So you identify the plane with the complex plane. You have a bunch of complex numbers, which are these increments along the edges. You sum the squares. And that's a function of the period you chose, because it depends, obviously, on the way you have embedded your lattice. But it turns out that if you choose this harmonic embedding, it depends only on tau. And if you solve the equation that this is equal to 0, it gives you exactly the right way to embed the lattice. So that's an exercise if you wanted to prove this. So what we get is one way to choose this embedding, which I want to find tau to call tau g. G for the green function is the one that makes the green function rotationally invariant. So this is coming from the simple random walk. Okay, if you are not a probabilist, but if you know circle packings, or if you have been here on Monday, you know that there is another way to embed a triangulation in the plane, which is doing circle packings. So this is a circle arrangement. There is a collection of disks. The interiors are disjoint, and the disks are tangent if and only if well, the disks are indexed by the vertices of the lattice, and they are tangent if and only if there is an edge. So this is the disk arrangement, and this is the lattice we have. So you see that there's a lot of rigidity, and again, if you choose the circle packing as a way to embed the graph, you can choose it in a periodic way, and it's rigid enough to fix for you the value of this period here. So again, it's a natural thing to do. It's to look at tau circle, and this comes from circle packing. So there's one thing that you need to be careful about, and maybe that's, well, that might be the important slide in the talk, but it's a stupid remark, which is that these two things, the tau for the random walk and the tau for the circle packing, in general, they are different. So it tells you that there is no canonical way to embed the lattice. And, well, you'll see a few examples where they are actually different, and you can compute them. Just one remark. So there is a natural way to build a random walk on the vertices of a circle packing in such a way that the scaling limit is Brownian motion and is isotropic. But it's not the simple random walk. It has jump rates which depend on the local geometry of the circles. So there will be a random walk giving this particular tau for the circles, but it's not the simple random walk. It's something else. Okay, something a little bit more towards the question of scaling limits, and that's the real motivation I had to look at these choices of embedding at the beginning. It's if you want to look at your favorite model of statistical mechanics and this triangulation. So, well, my favorite model of statistical mechanics is percolation, and what you want to do is to draw the triangulation of the plane in such a way that it is natural for percolation. So what does that mean? You want the scaling limit of percolation on the triangulation to be exactly SLE6, for instance. You look at the critical point, which is always 1/2, and you want to define a scaling limit. And one way to test that you are doing the right thing is to try to look at crossing probabilities of rectangle. So you fix a rectangle in the plane. So let's draw it here. You have your periodic triangulation here, which is not the triangle lattice, but it still is periodic. And you embed it with a mesh here. So the distance between two copies of the same pattern here is delta. And you want to let delta go to 0 and see if there is a limit as delta goes to 0. So the natural quantity that we saw several times since the last few weeks is to look at the probability that for side percolation on this triangulation you get a crossing by open vertices. Okay, and the question is, as delta goes to 0, what is the limit of this? Well, it converges as delta goes to 0 to some function of two things. Well, it depends on the rectangle, and it depends on the shape of the rectangle, but through the shape of the triangulations. And if you stretch the triangulation, you will stretch the rectangle accordingly. So you can write it like this. It depends on your choice of Euclidean rectangle and your choice of the embedding. And you say that a rectangle is balanced for the percolation if this is equal to 1/2. So the balanced rectangles are those that look like squares from the point of view of percolation. And then one natural thing that you might ask from your embedding is that the Euclidean squares should be balanced. And again, it gives you one value of the modulus of tau here, which makes the squares balanced. And if you have this, then you expect that the scaling limit has to be rotationally invariant, and then there's hope that maybe the scaling limit is SL. So you get this tau p, which comes from percolation. Okay, so that's three choices, and the last choice, it also has been mentioned several times this week. It's the conformal embedding. It's the thing you want to do if you want to look at complex analysis on a complex drawn on a plane. What you want to do is to start with the triangulation as a pattern, so as a combinatorial pattern. Start with a bunch of equilateral triangles and glue them together to form a surface using the triangulation as the pattern of the gluing. So you can do that, and the right way to do it is to see the periodic triangulation as the cover of a finite triangulation of the torus. And then what you get is you have finitely many triangles, you glue them together, and it gives you a Riemann surface which has the topology of the torus. And then you uniformize it. So you know that this is conformally equivalent to a torus, which is a quotient of C by a lattice, which is given by, well, Z plus some modulus times Z. So this is given by the Riemann mapping theorem, and it gives you, in particular, this tau sub delta, delta for the triangle. And so it's yet another choice. It's tau delta, which comes from the Riemann mapping theorem. Okay, I'm just saying nothing about the SL2Z action that makes it a little bit, well, ambiguous to speak about tau instead of the lattice, but you get this tau delta, which comes from the complex structure that you want to build out of the triangulation. So if you were there on Monday, you saw that one way to approach the complex structure that you get by gluing equilateral triangles is by looking at circle packings in a subdivision of our triangulation, and refining the subdivision, you get better and better approximation of the complex structure. So you start by a circle packing of the initial triangulation. So this is the same picture we saw before when defining the tau circle. And then you replace the triangulation by a refinement, and I will draw somewhere, and it will stay for a while here. So what you do as a refinement, you have several options, but the natural one is to replace each triangle by 4 triangles like this. And you circle pack this, and you get another circle packing. And here I drew the segments along the initial edges of your triangulation. Okay, so you can refine, and you refine again. And you get a very nice picture here, and this picture converges as the refinements are finer and finer to a continuous picture like this. So this is a nice way to get nice pictures, and it does converge, and it's a little bit involved to prove formally that it converges, but it does. So somehow there is a link between the circle packing choice of the modulus here and the conformal circle packing here, the conformal modulus here, which is what you get by refinement. So there's this arrow here, which tells you that if you refine this guy, you get this guy. The one problem, and we'll come back to it later, is that it's difficult to estimate at which speed you converge. So if you want to have a way to test if the embedding is the right one for percolation or for circle packing or for the conformal embedding, well, it's nice to be able to estimate with enough precision that the error you are doing comes from the probability and not from the way you embed. And by circle packing, well, it seems like it converges for a given pattern like a power of the smallest circle size, but well, it's difficult to use circle packings like this in a quantitative way. So what we have for now is this. We have a few ways to choose an embedding, and well, they have different features. The first one coming from the random walks, this is easy to compute. It's just solving a second degree equation, and everything is explicit. The one using circle packings, well, you can actually solve numerically for the location of the circles and the radii, and you can compute this numerically. So it's nice to start with and to draw pictures. The one from percolation is the one that we would like to understand better. It's the one that tells us how the percolation sees the triangulation. And the hope is that if you can answer this question, what is this value of tau p? Well, this answer should give you exactly the right amount of information to show that there is a scaling limit of percolation. So if you talk on the Ising model on isoradial graphs, the moment you understand that isoradiality is the right thing to look at for the Ising model, you know what to do to conclude, essentially, to get the conformal invariance. There should be some kind of building block coming here telling us that if we answer this question, then we know how to proceed. Yeah?
Here, does tau p exist?
No. It's clear that they all exist except this one. This one is assuming that there is a scaling limit. There is a unique tau p such that blah, blah, blah. Of course, if we knew that it existed, it would be better. But it exists. I'm sure of it. But. Okay, and this one, this tau delta, is the one that I want to talk about in what follows. It is defined using the uniformization theorem, but that's a little bit implicit. There's a general theorem saying that you can uniformize the Riemann surface, and it gives you some torus, but well, so far it's completely implicit. It's an existence theorem. And one natural question is if we can compute these explicitly, and the goal of what I will talk about next is how to compute this tau delta, this conformal modulus. Okay, just one remark. It's easy to see that these three, so the random walk one, the circle packing one, and the conformal one, in general they are distinct. And there is one particular lattice on which you can prove that they are distinct. It's the one for which the period is this. So you start with the first one I showed you, the Z2 plus 1 vertex, and you refine one of the triangles into three triangles. So for this, the random walk embedding is given by I times square root of 6/7. The circle packing embedding is given by I, because you can see easily that this changes nothing to the arrangement. It's just adding one circle. And this, I forget the exact numerical value. It's computable using the method I will show you. And it's neither square root of 6/7, neither 1. For percolation, in this particular case, it matches the one from the circle packing. So it's not clear that the percolation embedding and the circle packing embedding are different. And given that we can compute tau p only in the symmetric cases, I cannot really read it out. So it's a nice question if you want to think about it, if there is a link between circle packings and percolation in this respect. Okay, so that was what I was planning to say about embeddings of periodic lattices. Just, well, there has to be at least one theorem somewhere, so this is some slide with two theorems and one kind of heuristic about what follows. So the first theorem, which I want to call universality, but that's maybe a little bit ambitious to call it universality, is that this green arrow here, saying that if you refine the circle packing, you get the conformal embedding, that this is a general statement, that if you take any of these choices of the modulus, and you apply them to the refinement done like this, and you refine enough, you get the same limit. So whatever you do, if your graph looks locally like an equilateral triangulation, then all the embeddings chosen this way, they are very close to the conformal embedding. And this statement contains this arrow here, which tells you that, in fact, the conformal one is invariant by this splitting, which is easy to see because you can always glue 4 equilateral triangles into one equilateral triangle. So you get the same structure. And it's somehow attracting all the other ones. So this requires a separate proof for each of the arrows, but it always works, and the idea is always the same, that if locally you look like the equilateral triangulation, then locally the structure that you get has to be the same, and then you need to do some gluing and to have some estimates. The estimates come from different things in different cases, but the result is always the same, that if you refine more and more, you get the same embedding. Okay, maybe I should say a few words about the percolation case and about the second theorem here. If you want to look at scaling limits, you can do a little bit better than just refining the mesh. You can look at a joint limit where you refine the mesh, the triangles like this, and you rescale the lattice at the same time. And then, well, the theorem says that if you refine, if you do the subdivision and the scaling together, but provided the subdivision is done quick enough, then the scaling limit is the same as percolation. So just one word about the proof of this, but it will just be in one picture. And you will see that the proof is essentially the same for both theorems, except for the second one you need a little bit more quantitative estimates. So assume you have a triangulation containing somewhere one equilateral triangle and other triangles which are not equilateral, and you take a huge domain here. This is equilateral. You do this refinement by a piece of the equilateral lattice, and you do the same refinement on all the faces, so you get this fine approximation of the initial triangulation. And you want to look at the probability that in this box there is a crossing of open vertices. So, as we saw in the mini course the last 2 weeks by Clément, he proved Cardy's formula. And the key fact was that if you look at a conformal triangle and a point here, what you want to show is that the probability that this event occurs as a function of this point, this is a harmonic function. And the way you do it is you build this linear combination and you show that this is a holomorphic function. And the key fact is that the proof of this was essentially local. You have to show that the integral on circuits is 0, but you can restrict your attention to having, well, to the cases where this point is inside your equilateral triangle here. And if you take a point here, the whole proof that he explained and that Spinoff did at the beginning, it still works within this triangle. So the limit of this probability, it is harmonic in restriction to this triangle. And the limits of the linear combination is a holomorphic function inside this triangle. So it tells us that at least within this triangle, the scaling limit of percolation is the same, whatever you put on the outside. So it tells you that in any of all the other triangles, if you stretch them to make them equilateral, the scaling limit of percolation sees them as equilateral triangles. And this is exactly what you need if you want to show something like this. Like, you take percolation in a refinement, and you say that within each of the faces, you refine enough to have local conformal invariance up to the stretching that would make the triangle into an equilateral triangle. And that's exactly what you do if you want to compute this conformal embedding. So this is basically the proof, and you can do the same for the simple random walk. It converges to Brownian motion, and you do the same argument. For the cycle packing, it's a little bit more technical, but the scheme is the same. You look locally inside the face, you show that it looks like the usual triangular lattice, and then you glue things together. And of course, if you want to do this, you have to show something about the speed of convergence inside the triangle. If you have a good estimate on the speed, well, you can at the same time rescale the triangles. So I don't want to spend so much time on this, just to tell you that there is at least some universality with respect to the splittings of triangulations. And the heuristic is that if, for instance, you start with a random triangulation or something coming from a Poisson point process or something like that, it's expected that the precise way you build your embedding, it should not matter in the scaling limit. So it does in a finite deterministic case, but if you want to do that for a random triangulation of the torus, for instance, all these definitions, they should agree. And that's something that, as far as I know, we don't really understand, but it's something that, well, should make you less anxious about the fact that the embeddings are different. They are different in particular cases, but on average, they should give you the same answer. Okay, so that's it for the torus or periodic case. I want to say a few words about the case of the sphere and triangulations of the sphere. And it's good that I don't have to make an introduction on that, because we just got 2 talks with maps on the sphere. So this is essentially the 2-paragraph summary. What you do is you take a uniform triangulation of the sphere, and if you rescale the distance by n to the minus 1/4, it converges to the Brownian map as a metric space. And what you can do is you can take this triangulation as a pattern, and again, you can glue triangles, equilateral triangles, to make a complex structure on the sphere. And if you do that, it's expected that this now is connected to the Gaussian free field, that you should get something conformally invariant, which is somehow a common realization of the Brownian map and the Gaussian free field. And so one key step would be to understand really what it means to build this Riemann surface out of triangle, and whether we can get a good grasp of the kind of object that we get, that given by the Riemann mapping theorem or by the uniformization theorem, but if we can have something a little bit more computational that we can put our hands on. So as you saw, you can take a huge triangulation, and if you look online for ways to embed that, there's an artist that did something very nice. It's this, and you saw this picture already, so this is on the page of Nicolas Curien. So that's not the conformal embedding. It's the harmonic embedding, but it's embedded in some way in the sphere, which is not looking conformal at all. Okay, so now I want to give you one particular example where you can do everything from the beginning. So how do you sample a random triangulation? Well, there is one way. You can build trees, and you can do a bijection, and you can build something. And the last talk by Jeremy, you saw exactly what you get. There's a better way. There's an easier way, which is you use Google Images, and you look for random planar map, and you find this. So this is the planar map. It's the generic quadrangulation of the plane. It's the one that works for all the examples. So let's see what you can do with this map. It's a nice map. So let's try not to do things wrong. So there's this square here, then there is this vertex here, and there is this vertex here, and there is a square like this, and there is one more edge here. So this is the quadrangulation. There's a problem with my algorithm. You always get the same quadrangulation. So let's see what we can do. We want to glue triangles, so it's good if we have triangles. So let's build triangles. One way to do it is we add vertices at the center of each square, including one at infinity, and we do something like that. Like this. And we get a very nice triangulation, which happens to be with all even degrees, because you multiply each of the degrees here by 2. So it's a triangulation that comes with a natural coloring of the faces. If you want the dual graph of this triangulation, which is a graph of degree 3, it's bipartite. So we can color the triangles in 2 colors, like this. And okay, so that's what the kind of picture that you get. It's a triangulation of the plane with colors on the triangles. Okay, I will come back to the picture later. So what do you get if you uniformize the map using conformal map? Well, it turns out that you get something like this. I'm not sure the colors are well chosen, but when I tested yesterday, it looked better somehow. So this is the kind of embedding that you get. This is the conformal embedding of the map in the plane using equilateral triangles and a conformal map. So you can recognize the different vertices. So this, for instance, corresponds to the vertex of degree 5, which is here. And this here, this little structure here, is this path in the map here. And so you see that so random maps contain circles sometimes. If you look closely, this is really a Euclidean circle. And this comes from a symmetry in the map, which is maybe not apparent at the beginning. So there is this particular path in the map, which does something like this, if I didn't get it wrong. And this is an axis of symmetry of the map. If you reflect across this path, you get the same map. So this is sent to this, and this edge is sent to this. And well, you can check that everything works out, and you get some automorphism. And the trace of this automorphism is the fact that you have this circle here. So that's the kind of picture that you get. And my plan for the next 20 minutes is to tell you how to obtain this picture to essentially arbitrary precision, and then as an explicit formula using algebraic numbers. So what do you get if you take larger maps? Well, you get also nice pictures. You get things like this. It's nice. And as you can see, if you take your random map, well, it has degrees which are different from vertex to vertex. And one trace of this in the embedding is that some of the triangles are large, like this one, and some are very small here. There is kind of an accumulation point here. And of course, this corresponds to the fact that the Liouville measure is not the Lebesgue measure. It's singular, and it has accumulation points, and it has all this fractal structure. And already for small map, I think this one has something like 30 triangles or 40 triangles. You see this accumulation, and you see that, well, perhaps this would be a way to test the links between the matrix structure and the conformal structure to, well, already on a simulation to say that these accumulation points, they satisfy some scaling exponents. And of course, the problem is that if you want to use circle packings to approximate this picture, well, this difference of scales makes it very numerically unstable. So essentially, if you want to have good precision for the location of this point, you need the circles here to be very small, and it means that you need to split this a lot, and then you will have a lot of accumulation of extremely tiny circles here, and the number of circles has to be large because there are these different scales that you need to take care of. And then we come back to the problem of the speed of convergence of circle packings. It becomes awful to have control on the distance between the circle packing embedding and this guy. So this I said already, and essentially you can see what I'm going to talk about as a way to bypass this numerical problem. That's one possible motivation. If you want to draw this map, the discretization and subdivision, it's well, it will work asymptotically, but if you want enough precision, well, you will wait forever for the things to finish. So this is one possible motivation to be able to test the predictions of quantum gravity. You need enough precision to really say that what you see comes from the probability and not from the errors in the embedding. And so you need a precise embedding. So of course, well, there are other motivations, and the next 15 minutes I will tell you how to compute these maps and what happens and how they can be, well, given some explicit form. And it's a very nice piece of mathematics, which is not new, but I think it's not very well known by the probabilists, and maybe there's something to look at if we want to look at random maps in what follows. That might be something interesting. Okay, so let's come back to the initial setup. We start with a triangulation of some surface, say this one, of the plane. And I'm assuming for the moment that this triangulation has vertices of even degree. So the dual of the triangulation is bipartite, and that means that we can color these triangles in two colors. So there are here yellow triangles, and there are blackboard colored triangles, and they are arranged in this pattern. So this has an equivalent statement, which is that you can split the vertices of this triangulation into three classes. So there is the initial bipartition of the sides of the initial lattice, of the initial quadrangulation that we had here. So it has black and white vertices, like this. And it has these additional vertices, which are yellow here, which we use to split the faces into triangles. So one per initial face. And you can check that two vertices that are adjacent in the triangulation, they have different types. And along a triangle, you see the three types. And the order in which you see them depends on the color of the triangle. So on the yellow triangles, you see yellow, black, and white. And on the dark triangles, you see yellow, white, and black in this order. So what it means is that when you want to build the Riemann surface out of this pattern of triangles, well, you have one additional piece of information, which is the color of the triangle. And what you can do is, instead of gluing triangles, you can glue hemispheres of the Riemann sphere, where these points here correspond to the points 0, 1, and infinity. So what you do is, instead of having equilateral triangles, you take hemispheres with 3 points. So that's the same. Again, it's a conformal triangle. But you use the different hemisphere for the yellow triangles and for the black triangles. Okay, so far we didn't earn a lot, but what we get when you do that is that now we have a Riemann surface, which is obtained by gluing these triangles, and we have a function. So there is a function phi, which goes from the Riemann surface obtained from the triangulation, and it goes into the Riemann sphere. So let's call it S. So S is the Riemann sphere, and it sends each of the triangles into one of the hemispheres, and it sends the black vertices to 0, the white vertices to 1, and the yellow, so this is yellow now, sends the yellow to infinity. So it gives a little bit more explicit way to build this surface out of triangles, because we choose, so this is 0, this is 1, and this is infinity, and we choose to send the upper half plane to the yellow triangles and the lower half plane to the dark triangles. Or the opposite. Well, I have 50% chance of getting it right here, but you can do that. And so what you get really is a function that goes from the surface to the Riemann sphere. And that's saying that this is exactly giving a meromorphic function. So phi depends on the initial triangulation. It's a meromorphic function from the Riemann surface here to the Riemann sphere. So again, this is nothing new, and it was stated already on Monday that you can build this discovering map. So what do we get from this? Well, there is this theorem by Belyi saying that if you do that on some algebraic curve, there will be such a map here, which goes from your curve to the sphere, and which is ramified only above 0, 1, and infinity, which is exactly this kind of map. There's above all these points you get ramification because you have a degree here, and elsewhere the map is completely one-to-one locally. So there is this theorem telling you that surfaces that carry such a function that ramifies over 0, 1, and infinity are exactly the surfaces that are defined with coefficients that are algebraic numbers. So this is known as the Belyi theorem. It's not very difficult to prove, but it's kind of it's a deep theorem because it relates the geometric or complex analytic structure of a curve to the arithmetic nature of this curve. So we won't use this theorem as such, but we will use it as a guide to tell us which kind of map we are looking for. And mostly the fact that the coefficients are algebraic here tells us that there's a hope that we can compute them explicitly. So how do we do that? So let's look at the case of genus 0. So genus 0 is exactly this case. It's the case where the map here, the Riemann surface here, is the sphere itself. So what you have is some meromorphic function defined on the sphere. And so by compactness, it has finitely many poles. The poles correspond to exactly these points, the yellow points here. So this map has to be a rational fraction of the variable. So in this case, what we are looking for is a rational fraction, so from the sphere to the sphere, that has only these points as ramification points, and that is somehow adapted to the triangulation. So first, what does it mean that it's adapted to this? Well, if you have the function, you can just take the pre-image of the real line, of these three intervals in the real line, and what you get is the three kinds of edges on the map with their embedding. So if you want to draw a picture like I showed you just before, this picture, well, the map goes here from the plane to the Riemann sphere, and there's a point at infinity. And the color here is just given by the sign of the imaginary part of the function. So it's a nice way to give the picture. And the map will be adapted to the triangulation if the adjacency between these points here that you see, that are the points at which the function is critical, if they satisfy the adjacency coming from the map. So that's what you want. You want some algebraic, some rational fraction that will exhibit this topology when you draw the sign of the imaginary part. And you know a priori that, so by the Riemann mapping theorem, you know that there will be essentially a unique way to draw this, because that's the way obtained by gluing equilateral triangles. So that's what you want to find. So there are two ways to do that. You can look at the literature on Belyi functions, on dessin d'enfants, that's the object behind, and you can try to compute it, to compute everything explicitly. So what it means is you want to write phi of z as p of z over q of z. So the zeros of p are the zeros of phi, so they are these points. The zeros of q are the poles, so they correspond to these. And to obtain the points where you take value 1, you look at phi of z minus 1. And this should be some ratio r of z over q of z. And then you say that this should be given by a product of z minus zi to the power di, where zi are the location of these points and di are the degrees, because that's the ramification structure. And this corresponds to the factorization at these points here. So again, this should factorize. So you write the equality and you expand everything, and you get a bunch of algebraic equations that the coefficients of the polynomials should satisfy. And essentially, that's why the coefficients in the end will be algebraic. That's because you can write these equations in the coefficients. Except if you want to do that and you are a probabilist, then you fail because you don't know algebra, you don't know how to do these kinds of computations. And it's even more hopeless in the torus. So what you can do instead is you can do it numerically. So if you want to do it numerically, what you want is to find the location of these points. And essentially, what you want to do is you start with the location of the points, of these points and the points that are mapped to infinity. You build the rational fraction out of the zeros and the poles. So you just compute the ratio. And you look at what you see at the locations that should be sent to 1. And you want that the value is supposed to be 1 and the derivatives should be 0 to the right order. So the number of variables is the number of vertices of your triangulations. It's the locations of these points here. And the equations, well, you get one equation for each point here. And in addition, you get more equations for the derivatives. And if you count, you will see that each white point gives you its initial degree as a number of equations. So if you count it right, what you see is that this is the faces of t divided by 2. That's the number of conditions that you need to satisfy. And then you look at this minus this, and it gives you the number of degrees of freedom for this set of equations. And what you find is that it leaves 3 degrees of freedom, which is exactly the dimension of the automorphisms of the sphere. And that's how it should be, because you can still post-compose this by some automorphism of the sphere, and you get another solution. So this is nicely set up, and what you can do is you can now have a natural algorithm. You want to use a Newton algorithm to find enough precision for the coefficients. So you need a starting point, and you derive the starting point by any means necessary. So circle packing, so you ask a guy in the street to give you an initial value to start your Newton algorithm. And then you iterate the Newton algorithm, and it converges very quickly to the right coefficients. And then, because you know that the coefficients are algebraic, what you can do is you can identify their polynomials, the minimal polynomials, using something like lattice reduction. So I have no time to talk about lattice reduction. It's something it's almost like black magic. You start with an algebraic number, you shake it a little bit, and it gives you a polynomial that corresponds to this algebraic number. It's wonderful that you can do that, but I have no time to tell you exactly the details of this. But nevertheless, you can do it, and numerically you can do it, and it works. So what you get in the end is polynomials of which the roots are exactly the locations of the points that you want. And so you go through some numerical computation, but what you get in the end is really some polynomials with integer coefficients, and the roots of these are exactly what you want. So that's how the pictures I showed you are generated. You just apply this algorithm here, and it works and it gives you the right picture. Okay, what do you do in genus 1? Well, in genus 1, you need to read even more things about complex analysis, but mostly what you're looking for is some function phi which goes from the torus to the Riemann sphere. So this should be a meromorphic function on the torus, but one way to see it is to lift it to the plane and to look for some function phi t tilde which goes from C to the sphere and which is periodic with periods 1 and tau. It's the same thing as having a function on the torus. And such a function, this is what is known as an elliptic function. And an elliptic function is just a periodic meromorphic function like this. And they are very nicely classified. They are exactly rational fractions in the values and derivative of the Weierstrass P function with these periods. And again, so you can find huge amounts of literature on these, but these are two particular elliptic functions, and they are classified by, well, they are indexed by the periods here, and they generate the whole algebra of elliptic functions by using a rational function. So it's almost the same picture as before. We are looking for a rational fraction, except it's not in Z, it's in these two, P and P prime. And if you know about algebraic curves, these are the coordinates in the space in which your torus is an algebraic curve. So it's again, it's the same story. You want to find finitely many coefficients of some algebraic equation, and you have a given number of data. So here, the variables, you have all the locations of the points here, and you have one more, which is the modulus, because you don't know a priori what tau is. That's the whole point. That's what we want to compute. We want, in particular, to know the value of tau. So it's one more variable here that you can plug. The number of equations, it's exactly the same, because that was a local counting of the number of equations. And of course, the Euler relation gives you a slightly different outcome, because the genus now is 1 instead of 0. And if you compute the difference here, you find that it leaves you with 1 degree of freedom, which corresponds to shifts along the torus. So again, it's as it should be. There should be a unique, essentially unique choice of the modulus and the location of the points. And again, all these numbers should be given by polynomials with integer coefficients. And again, it works. You can do that. You can implement this on the torus. And if you do it on the torus, you see nice pictures like this. So this is a periodic triangulation of even degree. It's colored according to the parity of the triangle. And what I did is I ran exactly this algorithm. I circle packed it to get an approximation, and then I used the Newton fixed point algorithm to find the exact values. And then you can check, so I didn't put it on the slides, but you can check that if you plug the outcome here into the lattice reduction, you do find the minimal polynomial corresponding to all these. And it works, and you get the exact values of the points. So you see more nice pictures like this. And this is for a random triangulation of the torus. I forget the number of triangles, but it's something like 30. And again, on the torus, well, we expect to have a scaling limit which is non-degenerate in the conformal way, in the conformal sense, and that's what we see. We see that there are large triangles and small triangles, but it looks like at least the shape of the triangle is not becoming very flat, and it's not becoming very tall. It seems that the global geometry is tight. So I want to end on this. One thing that, so it was one question that Jeremy had in the previous talk, it's how can you control the conformal modulus of the torus that you get using random triangulation. And if you start to look at what you need to exclude, you want to find a triangulation of the torus for which the modulus is bad. It's looking like something very thin. And essentially, the only thing you can think of to do that is a triangulation like this. So it has one vertex of huge degree, and it's very asymmetrical. So you see it has this particular direction along which the embedding has to be very tall, because the random walk, for instance, it will want to follow the triangle, so it will want to become very horizontal. But already, so this has degree something like 30. And if you want to do circle packings with degree 30, you know that it's kind of unstable, but if you shake it in the right direction, you see the thing converge again. And you see that the modulus that you get here is not awful. It's still reasonable. So really what you need to have some tau which remains tight it's not much on the triangulation. It's very difficult to build the triangulation for which it goes to infinity in this direction. So at least it gives some evidence that it should remain tight if you look at a random triangulation. Okay, that's essentially what I wanted to say. So thanks for your attention.
Questions?
Yes. So in your earlier few pictures just now at the end, so you did the actual numeric
Yep.
approximation
Yes.
and the circle packing approximation.
Yes.
How close were they? I was curious whether the...
Well, they were like a power of the size of the disks, essentially. So if you count the number of subdivisions like this, it converges exponentially fast in the number of times you apply this. And well, essentially it should be like this because the singularity should be a power, so that's the kind of error you have if you look at the proof. But it's an observation and it's a natural conjecture that this is what you should see. But if you want to have something uniform as a function of the maximal degree or something like that for a random map, I don't know how to do it. It might be doable. Yeah.
So I know we don't know that tau p exists in general, but is there any reason to believe it would be algebraic?
No. That's the quick answer. There's no reason to expect that.
That J of it would be algebraic, which is what you're getting here.
Yeah, so if it corresponds to circle packings, then yes. But no, there's no clear reason to hope that it would be the same thing. But we know no value of it except in the case of the triangular lattice. Then it's algebraic. So
Yeah, I was just imagining that you could imagine the framework of a proof using a holomorphic observable where somehow you had to solve some polynomial equations to make various...
Now, if you try to do that, you will find that the equations tell you that you have the triangular lattice. It will tell you that all the local triangles have to be equilateral and that the degrees are 6 and everything is very rigid. So it would be nice to have such an approach that could predict that it's algebraic, but as far as I know, it's not possible.
Other questions? So let's thank Vincent and the other speakers.